Welcome back to the Deep Dive. Today, we're tackling a really foundational piece, Chapter 25 from the Feynman Lectures on Physics, Vol.2. The title is Electrodynamics in Relativistic Notation.
That's right. And it sounds maybe a bit intimidating, but the goal is actually, well, simplification. It's about seeing how electricity and magnetism, which can seem complicated, look much cleaner, much more elegant when you use the language of special relativity.
So we're talking about making these physics laws look the same no matter how you're moving, right? That's the core principle of relativity.
Exactly. The laws of physics shouldn't change just because you're on a moving train, metaphorically speaking. And Maxwell's equations for E and M are actually compatible with this, but it wasn't obvious. This chapter shows why they're compatible, using this four-dimensional perspective.
And Feynman makes things a bit easier notationally, doesn't he? Setting the speed of light $2 to 1.
Yes, in several sections he does that. It helps clear away the constants so you can really see the structure. The hunt is for invariance equations that keep their form under a Lorentz transformation.
Okay, so let's get into the toolkit. We need new tools for this relativistic view. We can't just use our standard 3D vectors anymore.
Right. We need to treat time on a similar footing to space. That leads us to the idea of a four-vector. Think of it as an object, let's call it a mood, that has four parts. One time component, a parter, and the three familiar space components, ax, xi.
And you gave a key example, the form momentum.
Yes, Pum-U-Hell, this is maybe the most important one early on. It takes energy, 8a polar, which feels like a scalar, and the momentum vector, math BSP, and says, no, these are actually just different parts of the same four vector.
Yeah.
So P-mu is the scale APR, assuming 2 APO. Energy is the time part, momentum is the space part. There's also the four velocity, OMU, which is related.
Okay, so we have these new four-dimensional objects. How do we measure them? Like, in 3D, we know distance squared, sex by dollars plus y2 plus z22 doesn't change if you just rotate your view.
Yeah.
What's the equivalent unchanging quantity, the invariant, in 4 dimensions when you do a Lorentz transformation?
Ah, good question. And this is where space-time gets, well, a little weird compared to just space. The invariant isn't just the sum of squares. The invariant length squared of a four-vector or mu is actually a1 open 8 by a2 a's to it. Notice the minus signs for the space parts.
Minus sign, so time component squared minus the space component squared.
Exactly. And that structure defines the four-dimensional scalar product between two four vectors, say a2 and $. It's 8bax, bxax, a by a's, bci. That combination, b equal AAV, gives you a single number, a scalar, that is invariant. Every observer, no matter their constant velocity, will calculate the same number for that scalar product. It's fundamental.
Okay, that sounds powerful. And the chapter immediately shows us how powerful with a real physics problem, right? The antiproton creation.
Yeah, this is a great example. The reaction is proton plus proton goes to proton, proton, proton plus an antiproton, pp plus p plus p plus p plus bar q plus p of the matter. You're creating new matter and antimatter.
Which takes a lot of energy. And calculating the minimum energy needed using old school methods sounds painful.
It's a nightmare in the lab frame, where one proton hits a stationary one. The calculations get incredibly messy with relativistic momentum, but we have a shortcut now.
The form momentum. We know the total form momentum has to be conserved.
Precisely. P-text total before 2, and we also know that the square of the length of any four vector is invariant. So let's take the length squared of the total form momentum.
So calculate Vt22 and set it equal to over22. And that number must be the same in any frame.
Exactly the same. So we choose the easiest frame, the center of mass frame or CM frame. Before the collision, the total momentum there is 0 by definition. After the collision, at threshold, all the resulting particles are created essentially at rest in the CM frame. Calculating the total form momentum squared there is, well, relatively simple. It just involves the rest masses.
Okay, so you calculate this invariant number in the easy CM frame.
Then you jump back to the lab frame. The expression for the total form momentum squared looks much more complicated there, involving the unknown initial energy we want to find. But we know it must equal the simple number we found in the CM frame.
Because it's invariant. It's the same number, so you just solve for the energy.
And out pops the answer. The minimum total energy needed in the lab frame turns out to be $7, where dollars is the proton mass. That translates to about 6.6 GeV of kinetic energy for the incoming proton.
Wow. And that explained why they needed huge accelerators like the Bevatron back then. You couldn't make antiprotons without that kind of energy.
It perfectly shows the power. A hideously complex problem becomes manageable because we exploited an invariant quantity. That's the beauty of the formalism.
Okay, so that's the power of the vectors. Now, how do we apply this to the actual laws of E and M? We need calculus, right? Derivatives in 4 dimensions.
We do. We need the four-dimensional gradient operator. It's usually written as a hablamu. And just like the scalar product, it has a crucial structure. Partial partial t, partial partial x, partial partial y, partial partial v dogs. Notice those minus signs again on the space derivatives. They are essential for it to transform correctly under Lorentz transformations.
Got it. Time derivative is positive, space derivatives are negative in the definition. How does this simplify things? Let's take charge conservation.
Okay. First, we need to unify the sources of electric and magnetic fields. Charge density, AOROs, and current density, math BFJ. We combine them into the four-vector current density, AORO math BF. Again, BF is the time-like part, math BFJ is the space-like part, assuming 2 HAG.
So sources are now a four-vector. What happens when we apply the four gradient to it?
This is where it gets really neat. In 3D, charge conservation is partial rho, partial t plus nabla and partial o dollars. Kind of cumbersome. But if you take the four-divergence, which is applying a nabla mu to J or O using the four-vector scalar product rule. So
let me guess. It simplifies.
it collapses. The whole thing just becomes an Lamu J mu. That single compact equation is the law of conservation of charge, written in a way that is manifestly invariant under Lorentz transformations. It holds in all frames.
Zero. That's elegant. Okay, one more piece of calculus machinery mentioned. The D'Alembert box squared symbol.
Right, square spark here. This is basically the four-dimensional version of the Laplacian operator that you see in wave equations. It's defined as Frascheralde 10 Vol.2. The time derivative part minus the space derivative part. It's naturally suited for wave phenomena in spacetime.
And this operator is key to simplifying Maxwell's equations themselves.
It is. But first, we need one final unification. We unified the sources into JMU. Now we need to unify the potentials. The scalar potential parent in, related to voltage, and the vector potential math via T related to magnetic fields.
These always felt like separate things in introductory E&M.
They did. But relativity reveals they are not. They are components of a single entity. The four potential, a mu, defined as AMU math BFA, again with $2. AMU is the time component, math BFA is the space component. They transform together under Lorentz transformations.
So just like energy and momentum, AMU math BFAA are intrinsically linked aspects of the same underlying field potential.
That's the profound insight. And now we combine everything. We have the four potential AMU, the four current JAMU, and the D'Alembert operator squared 2 tunneled is.
What happens?
Maxwell's equations, specifically the wave equations for the potentials, which are usually written as two coupled, somewhat messy equations, they collapse into one single, stunningly simple equation.
Which is?
Circle 2 AMU, frac 1 epsilon. We need the epsilon dollars if we're not using units where it's 1.
Wow. Okay, say that again. Box squared of the four potential equals a four current times a constant.
That's it. Square 2 AMU frac 1 epsilon. This one equation contains the dynamics of both the scalar potential life phi and the vector potential math BFA, driven by both charge density O phi and current density math BFJ. And because it's written entirely in terms of four vectors and invariant operators, its form is manifestly the same in all inertial reference frames. It proves the relativistic invariance of electrodynamics.
That's incredible. Historically, Maxwell wrote his equations before Einstein's relativity, right? But the structure was already there, hidden.
Exactly. Relativity revealed the underlying symmetry that was always present in Maxwell's theory. This equation just makes it blindingly obvious.
And quickly, the chapter shows how useful this is for calculations, too. Like finding the potentials of a moving charge.
Yeah, another great example. If you have a charge taller just sitting still in its own frame, the potentials are super simple. PFI is just the Coulomb potential toplo, and the vector potential math BFA is 0.
Okay, easy in the rest frame.
Now, you want the potentials phi in the lab frame somewhere where the charge is moving. Since we know 1 nu phi is a four-vector, we know exactly how its components must transform when we go from frame to Zallar dollars. We just apply the standard Lorentz transformation formulas to the components.
No complex derivations needed, just transform the
Let's just transform the vector and out pop the correct, well-known expressions for phi and math BFA for a moving charge in the lab frame, the ones that are usually derived with much more effort. It confirms the whole approach. The four-vector machinery isn't just elegant, it's computationally powerful and guarantees consistency with relativity.
So the big takeaway is this profound simplification. It's not just about notation, is it? It's about revealing something deep.
Absolutely. It reveals the inherent four-dimensional nature of electromagnetism. The laws want to be written this way. The simplicity isn't a trick, it's uncovering the true structure. And Feynman emphasizes this principle of relativity, this requirement that laws look the same in all frames. isn't just for E&M, it applies to all laws of physics. Forces governing mesons, neutrinos, everything must obey these Lorentz transformation rules.
He even pushes it further with this idea of unworldliness.
Yeah.
What's that about?
It's a fascinating, almost philosophical point. He suggests that maybe every fundamental law of nature can be expressed by finding some scalar quantity without new dollars, which must be zero. So like for Newton's second law, $5. If 5 on is not zero, you could define that difference as the unworldliness dealer. The law of nature is then simply U dollars.
So for electrodynamics, is dual rule related to that main equation?
Essentially, yes. You could construct an invariant scalar nu dollar based on square-2 amu frofrock abemo. The law of electrodynamics is that this particular dollar must be zero. It makes you wonder, could other complex areas of physics, maybe even beyond what we know now, ultimately boil down to finding the right invariant scalar $2 and setting it to zero?
A very provocative thought. Finding the ultimate simplicity. Okay, so let's quickly recap this deep dive. We saw how four vectors merge space and time components, like energy and momentum, in Pumo.
We saw the crucial role of the invariant scalar product with its minus signs for space, allowing us to solve hard problems like the antiproton production threshold energy about 6.6 GeV kinetic.
And the four gradient nabla and four current J-mu simplified charge conservation to ambla nabla dollars.
And finally, the stunning simplification of Maxwell's wave equations into the single elegant invariant equation. Square-2 amu fre when epsilon J-mu.
Revealing the deep symmetry between electricity, magnetism, and relativity.
Thank you for joining us on this exploration of symmetry and simplification. The next time you face something that looks incredibly complex, remember Feynman's approach here. Sometimes the right perspective, the right notation, can reveal an underlying elegance you never expected. We'll talk to you next time on The Deep Dive.